This is the estuary at Porthmadog in North Wales. It's just like any of the dozens of estuaries you can find round the coasts of Britain. The sand flats show that there's an enormous expanse of sediment here, and there's lots more under the flat marshy ground behind the causeway leading out of Porthmadog. A lot of sediment's obviously accumulating here. And the question is, where does it come from and how does it get here? Well, the obvious short answer is that it comes down from the mountains inland, brought down by rivers. In this program, we're going to be looking at some of the processes of rock weathering and erosion and of sediment transport and deposition. In other words, we'll be looking at the surface processes part of the rock cycle. Now, to do that, we'll take one of the two rivers that flows into this estuary here, the Afon Glaslyn, the River Glaslyn, and we'll follow it down to here from its source near the summit of Snowdon. Snowdon is the highest mountain in this part of Britain, just over 1,000 meters high. You probably recognize this kind of scenery. It's typical of any mountainous area that's been glaciated. These great amphitheaters, the sharp ridges, the U-shaped valleys, they were all carved out by glaciers during the Ice Age. The hollows that were scooped out by ice are now filled by lakes, and some of the lakes are dammed by boulder clay, left behind as the ice melted. And of course, streams and rivers now flow in the valleys. Where the slopes are steep, the weathering process, the breakdown of the rocks, is mainly a mechanical one. In winter, water freezes in cracks in the rocks, expands and splits the rocks apart. Blocks are continually falling down to form jumbled masses of scree. And rainwater's acid, and it also attacks the rocks chemically, but that's a much less obvious process. Chemical weathering is helped by vegetation, because plants extract nutrients from rocks, and that helps to generate a soil cover. Now, all these materials, the rock fragments and the soil, fall and roll and slide and are washed gradually down the slopes and into the streams and the rivers. And then they're transported on down towards the sea. So this region's obviously one of active erosion and removal of rock materials. This small lake, Glaslyn Lake, just below the summit of Snowdon itself, is the start of our river. It's kept filled by water trickling and cascading down the sheer walls of this enormous amphitheatre. Now let's go and take a closer look at the stream, just below its outlet from the lake. The stream cascades down this steep slope below the lake. It's little more than a mountain stream at this stage, and it flows into a second lake that's filling another glacial hollow. On the other side of the valley, there's another great sheer wall carved by ice, and screes are accumulating near the bottom. This is a good place to look at the stream bed. Well, it's a typical mountain stream. There's a good deal of bare rock and a chaotic jumble of assorted angular blocks of all shapes and sizes. But let's just look at that matter of shape. You may have noticed, actually, that some of the blocks have got a tabular or slabby shape. And that actually is because of the nature of the rocks from which they've come. These are very ancient rocks, lower Paleozoic in age, old sedimentary and volcanic rocks, and they've been weakly metamorphosed by heat and pressure. And that accounts for the slabby nature of the rocks. Now, there's another thing. You may have noticed some of the white streaks in some of the rock faces. Now, those are veins of quartz, and quartz is the most resistant of the common rock-forming minerals. You can find blocks of it in the stream bed here. And of course, quartz, as small crystals and grains, is also a mineral constituent of these rocks. It's early autumn now, and there's not a great deal of water in this stream. But winter storms and spring thaws can transform it into a raging torrent. And then a lot of these blocks will be moved on down. They're too big to be transported as anything other than bedload. That's to say, they're rolled and tumbled down along the rough bed of the stream, especially where it's steep. And as the blocks roll and jostle each other, the edges and the corners get worn down and the blocks get more rounded. And of course, smaller fragments also get carried down. Well, most streams don't start in lakes. They begin in situations like this. Water's percolated into the rocks above me and behind me, and it's seeping out of the ground in springs to make boggy ground like this. There's another spring behind me there in the reeds, and another one a little further on down the valley. And the streams from these springs join together and flow on down the hill. That spring-fed stream joins another straighter tributary coming in from the right. And that one rises only a little way further up that valley, just where it disappears from view. It looks as though it's the main stream, but it's not. That's the Glaslyn, directly across the valley, cascading down the steep rocky channel. It's quite a way down from its source near Snowdon, and it's carrying a lot less water than you might expect. You probably remember the reason for that from TV8. Much of the water's been diverted into the black pipeline down to the small hydroelectric power station in the bottom of the valley. Looking at this valley, you get a good impression of the immense erosive power of the ice that's responsible for this landscaping. Even in flood, these little streams could never have produced valleys like this. So the rivers and streams, in fact, are flowing in a valley that was gouged out by glaciers. Well, this is still in the upper reaches of the Glaslyn and its tributaries, and the beds of these streams will be very much like what we've looked at already, full of a jumble of angular blocks of rock. But if we look further downstream, you can see a change. The river's wider because it's been joined by several tributaries, and it's flowing through a flat meadowed area. If you think back to that little delta we saw earlier, you can see what's happened here. As the river enters the lake, it slows down and deposits sediments. And those sediments are progressively silting up the lake until it's now only about half its original size. In other words, that flat meadowed area was lake only a few thousand years ago. Now let's have a closer look at the material being deposited in that situation. Actually, we'll go down to the next lake along, a few kilometers downstream, because it's more accessible. Well, this flat meadow is underlain by sediments that have been dumped here as the river enters the lake. And this shingle bank gives us a pretty good idea of what those sediments are. The fragments are smaller and more rounded than anything we've seen before, and there's lots of nice flat pebbles here, which you'd expect considering the slabby nature of the rocks they've come from. In fact, they're ideal for skimming. And this is a good place to begin to see some of the features of sorting of sediments where this river enters the lake. Just down here, where the flow is fairly rapid, you've got shingle in the bed, and further downstream, where the flow is beginning to get slower, you've got sands. And then finally, right out in the lake itself, where the energy of the environment's very low, the water's virtually still, that's where you'd expect to find the clays settling out of suspension. And if Britain was a more Arctic country, that's where you'd expect to find varved clays. And that leads us into a little problem. If most of the sediment's been deposited by the river as it enters the lake, what would you expect to find making up the bed of the river at the other end of the lake, below the outlet? Well, let's go and look. This is about 1 kilometre down from the lake outlet. There's obviously no shingle in the bed, just big, angular blocks, and they've obviously come from a local source. And it's worth just thinking about the implications of that for a moment. Wherever a river flows into a lake, it dumps virtually all of its sediment, and virtually none gets out at the other end. In other words, lakes act as very efficient sediment traps. And so where a river leaves a lake, it starts again with a new sediment load. Carrying on downstream, at the village of Bethgelert, the Afon Glaslyn is joined by a sizable tributary coming in from the north. And below the confluence, the river's got more water in it, because two streams have joined forces. But what's important here is that we've also got two contrasted flow regimes, and these are quite characteristic of the middle reaches of any river. Here, there's very rapid and turbulent flow. The channel's shallow and it's partly obstructed by those big blocks. Down there, the flow's rather more sedate. It's slower and less turbulent. The channel's wider and it's deeper. And there are bends in the river here too, and that has another implication for contrast in the flow regimes. On the outside of this bend, the water flows rapid and turbulent, and the flow becomes slower as you move into the shallow water. And all these contrasts in the flow regime means contrasted energies of environment, and that's got obvious implications for the types of sediment you're going to find. Over here, where the energy's high, the bed's mainly of coarse shingle. And as you move into the lower energy environment here, you get an increasing amount of finer material being laid down. And of course there are local changes as well. Just in the lee of this rock, very conveniently, there's a little eddy shadow, if you like, a low energy patch. And there, fine sediment is being deposited, or at any rate finer sediment, and on either side of it, the high energy channels, so to speak, are sweeping the fine material on downstream. Well, let's just look at the sediments making up the riverbed more closely. Most of the materials, the grey, flat shingle that you'd expect knowing the rocks from which they've come. And there's also some bits of quartz. And what about the range of grain sizes that we've got represented here? Well, we've got big fragments, and they come down through pieces a few centimetres across, right down to bits that are a millimetre or even less in size. Not particularly good sorting, and if you sieve the sediment from here, you can make that more quantitative using a histogram. Now, of course, it's not really surprising you've got this range of grain sizes here, considering the range of energies of environment that you've got. And as well, you have to remember that you get seasonal fluctuations in the river depending on the rainfall. Well, now let's just look at the way in which the sediment's transported here. If I pick up some of this finer material and sprinkle it on the riverbed in a convenient spot, you can see that for yourself. The material's all being carried in the bed load, either by rolling or by bouncing. And it travels intermittently because, of course, there's intermittent turbulence. And this is quite interesting. There's a small sheltered patch, just like there was in the main river, where there's a temporary low energy patch and the sediment accumulates. Very little material is being deposited from suspension here because, of course, the energy environment's much too high, and all the fine material is being carried on downstream. These are the lower reaches of the Afon Glaslyn, the flat floodplain across which the river meanders on its way to the estuary. The river's wide and deep here, and the flow of water is much smoother than we've seen before. And that's reflected in the sediments. These sands are quite well sorted. If you were to look at a histogram of a sieved sample from here and compare it with what you've seen before, there's quite a difference. The peaks shifted to the smaller grain sizes, and it's also got much narrower. But there's another important difference about these sediments. If you look closely at these sands, they're mostly made up of quartz particles, whereas the other sediments were mostly made up of rock fragments. In other words, what's happened here is that the rocks have been broken down by now to their constituent minerals, and as quartz is the most resistant of those minerals, it's quartz that's making up the bulk of these sands. Well, these sands have been brought down from the higher energy environment upstream, sorted out from there, brought down, deposited here where the energy is lower. And eventually, they'll be moved on downstream when the flow of the river increases, perhaps because of increased rainfall in the mountains. But not all of the sand's going to move on downstream. Take a look in the bank just here. Well, it's not difficult to see why there are stratified sediments here, when you bear in mind that this is a floodplain. When the river floods, sediments get spread out over the surrounding meadows, so that from time to time a new layer is added to this sequence, and it covers the vegetation that's grown on the layer immediately below. You're looking at a sedimentary rock in the making. This floodplain merges with the upper parts of the estuary, and this flat landscape is clearly the result of deposition of sediments. Quite a contrast to the mountains behind, which represent a landscape of erosion. Vegetation on the floodplain and in the upper estuary tends to trap and bind the sediment, and all that helps to build up the level. You can see the other river flowing into this plain as well. And it's easy enough to see the main channel of the Afon Glaslyn on the northern side of the estuary. So now you see how at least some of the sands that go to make up these sand flats have got down here, brought in by the River Glaslyn. Some's also been brought down by the other river that flows into this estuary, and some has been produced by wave and current action along the coast, brought up along the coast and then deposited here. But these sands are too coarse to have been brought down here in suspension. They've mostly been carried in the bedload, rolled or bounced along the bed of the river. So what's happened to the material that's been brought down in suspension? It didn't all get left behind in those lakes, so where is it? And here it is. And there's no doubt that this little harbour provides the ideal quiet environment for these fine muds to settle out of suspension. And there's no doubt that this is the fine suspended load of the river. If I were to drop a handful of this into water, the muddy cloud you'd see would straight away tell you that it only needs a small amount of disturbance in the water to keep that material from settling out of suspension. These muds are made up of minute particles of clay minerals. They're the finest size fraction of the material produced by the breakdown of rocks. So all these sediments, the sands and the muds, have been produced by the breakdown of older rocks. And they've been progressively sorted into different size fractions as they've been transported by rivers down towards the sea. Well, all the things that we've been looking at have really only happened in the last 20,000 years or so, since the last glaciers melted. And that's really only a very small part of geological time. But all these sediments, the sands and the muds, are the raw materials of sedimentary rocks. And so by studying the processes of sedimentation and comparing them with a record in the sedimentary rocks, we can work out what conditions were like in different places and at different times in the geological past. And that's what the principle of uniformitarianism is all about.
Yeah.
Because all of it boils down to that. Now, I'm not reasonably doubtful about the fact that he did it. You are. So what we need to work out is what do we mean by reasonable doubt? You seem to want to actually see it happen, and this cannot happen.
What I mean by reasonable doubt is that there is a possibility that somebody else other than
knocked
him
or
could have done it.
And so they went on for over an hour, and no one changed sides. It is doubtful whether they would ever have reached a verdict.